In section 2.5, we're going to continue talking about zeros of polynomial functions. Rational zero theorem, finding zeros, solve polynomial equations, Descartes' rule of signs. I know that that looks like D-E-S-C-A-R-T-E-S. A lot of students not knowing how to pronounce it assume that it's pronounced Descartes or Descartes, but it's pronounced Descartes is how you pronounce that. I don't know why, but that's how you pronounce his name. It's a famous mathematician who was Swiss, maybe? I think he was from Switzerland. I don't remember. Anyway, make sure you answer the question why you think it's important. The rational zero theorem. Okay, so we have a polynomial that has integer coefficients. Remember integers, those are the 0, 1, 2, 3, etc., and -1, -2, -3, etc. No fractions, no decimals, no square roots, whatever. It needs to have integer coefficients. And P divided by Q is a rational zero. Then P is a factor of the constant term here, and Q is a factor of the leading coefficient. Okay, what does that mean? Suppose we have 7x squared plus 2x minus 8. If I'm trying to find potential rational zeros, what I can do is figure out my factors of 8. That would be a +1 and a -1, and a +2 and a -2, and a +4 and a -4, and a +8 and a -8. So those would be numbers that would go on top of a fraction, and then I would divide that by all the factors of 7. So each of these numbers divided by each of those numbers would give me all the potential rational zeros of this polynomial. How does that, or why do we care about that? Well, if you don't have a calculator, and there will be portions of the AP exam where you're not allowed to use a calculator. If you don't have a calculator and you're trying to factor something or solve something that is maybe an x to the 4th, or I don't know, has x to the 7th, whatever, this is a tool to help you start the factoring process by giving you potential zeros of that polynomial. If we didn't have a place to start, then it would be just a matter of randomly guessing, and the problem with that is there are an infinite number of numbers that we could randomly guess, and we could be there an awfully long time before we narrowed it down to one that was a zero, one that actually worked. So by using the rational zero theorem, it allows us to narrow down the list of numbers to guess. We're still guessing, not going to lie. We're still going to guess and check, but it narrows down the list of the pool of numbers from which to choose from. List all possible rational zeros. So first thing we have to check and make sure each of these numbers is an integer, which they all are. So then we can use the rational zero theorem. So first of all, we're going to list all the possible factors of our -3. and 1 goes in evenly, and so does 3. And then we're going to list all the possible factors of 4. So 1 goes in evenly, 2 goes in evenly, and 4 goes in evenly. And then I'm going to take each one of these and divide it by each one of those. So I'm going to take my 1 and divide it by 1. 1 and divide it by 2. I'll worry about the pluses and minuses in a minute. My 1, I'm going to divide it by 4. Okay, then I'm not done because I still have to do my 3's. Just pick a different color. So now I need to take my 3's and divide it by each one of these. So I'm going to take 3 and divide it by 1, 3 and divide it by 2, and 3 and divide it by 4. We're going to reduce. So 1 divided by 1 is 1. 1/4. 3 divided by 1 is 3. 3 halves and 3/4. Now, I said we would worry about our pluses and minuses in a minute. So here's the thing. This could be a positive 1 or a negative 1. This could also be a positive 1 or a negative 1. So the combination, I could have a positive 1 divided by a positive 1. I could have a positive 1 divided by a negative 1. I could have a negative 1 divided by a positive 1, or a negative 1 divided by a negative 1. But no need to worry, because when you reduce those, you end up with a positive 1, a negative 1 again, and a positive 1 again. So really, we can ignore those two situations and just worry about the positive 1 and the negative 1. Long story short, all we need to worry about is plus or minus 1, plus or minus 1/2, plus or minus 1/4, plus or minus, plus or minus. So how many numbers do we actually have sitting here? So a lot of students count them 1, 2, 3, 4, 5, 6, but they're only counting the positives. They're forgetting about the negatives. So you have 6 positive numbers, and you also have 6 negative numbers. So altogether, you have 12 possibilities. And before you think that that's a great number of numbers to guess and check and try, narrow that down from an infinite number of numbers, and you'll see why this is very helpful. So you have 12 possibilities versus an infinite number of possibilities. All right, so now it says find all of the zeros. So we are going to first list all of the possible zeros and then check to see which one of them actually works. It could be more than one. We'll just see how it goes. So first thing we're going to do is all of the factors of the constant. And we're going to divide those by all of the factors of the leading coefficient. So when we take 1 divided by 1, we get 1. 2 divided by 1, we get 2. So when we simplify that, we end up with plus or minus 1, plus or minus 2. So 4 possibilities. And we're going to check. We're just going to start with one of them. Doesn't matter. So we've got a positive 1, a negative 1, a positive 2. That doesn't mean all of these will be solutions. It just means those 4 numbers are potential zeros. Okay. So now is the guess and check part. So we're going to pick one of them. Okay. I'll just randomly pick one. I'll start with 1. Okay. So I'm going to start with 1. 1. And I'm going to use synthetic division. I'm going to check to see if it's indeed a 0. So bring down the 1, multiply, add, multiply, add, multiply, add. That is not 0, so we can rule out 1 as a 0. Okay, so it's not a 0. Let's try -1. And I'm just going in order just for ease. It really doesn't matter which order you do these. You're just guessing until you find one that works. When I say one that works, what I mean is where we end up with a 0 there. Okay, so -1 also did not work. So now I'm going to try the next one, 2. So 1, 1, -5, 2. And we just keep going until we find a 0. That should be -2, and that should be -5, and that should be -2. Not sure why I did it for one of them and not the other, but okay. So 2, and there we go. That's what we were looking for, a 0. So that tells me that 2 is a 0. So x equals 2, that's a 0. X minus 2 is a factor, is the corresponding factor. And I also have, it's hard to see down here, but this is my remainder, my constant, my x, and my x squared. So x squared plus 3x plus 1, that equals 0. So now we have x squared plus 3x plus 1 equals 0. And because it's now quadratic, the x squared is quadratic, we can use quadratic techniques to solve it. I don't believe it's factorable. It's not factorable, in fact. So we're going to use the quadratic formula on the next slide. So we have x squared plus 3x plus 1. And what was the other one? X minus 2, I believe. Yep. Okay. So ax squared bx c. So I'm going to use the quadratic formula. -3 plus or minus the square root b squared minus 4 times a times c 2a. And we simplify that, plus or minus 9 minus 4 over 2 square root 5 over 2. Most of the time, I won't even say most of the time, I don't even know. Most of the time they're going to want, so here's my original x equals 2, and then here are my other two answers. A lot of times they're going to want an exact answer. Occasionally they're going to want a decimal approximation. So if they say approximately rounded to X amount of decimal places, then you would plug it into the calculator. Otherwise, just simplify and leave it like that. Since they did not tell us they wanted a decimal, we're going to leave it like that. Okay. What else? polynomial is degree n, counting multiple roots, meaning multiplicity greater than 1, then the equation will always have n roots. What does that mean? If I have an x to the 5th power, I will have 5 roots, 5 solutions, 5 zeros. They could be duplicates. We could have multiplicity of 5, but there's going to be 5 of them, including if you include the multiplicities. If you have a complex number as a root, then the conjugate will also be the root. Remember, imaginary roots, if they exist, occur in conjugate pairs. So what does that mean? If I have x equals 7 plus 2i as a root, then I'm also going to have 7 minus 2i as a root. They don't always tell you both of them. They may just say, oh, by the way, 7 plus 2i is a root. They assume you realize that if they tell you 7 plus 2i is a root, then 7 minus 2i is also a root because of this property right there. Okay. All right, solve. First thing we have to do is figure out the possible roots. Okay. Check the possible roots and see if one of them is an actual root. Okay, so let's start there. So we have plus or minus, so we're looking at our 13 now, plus or minus 1, plus or minus 13, and then this will give me our plus or minus 1. So when we simplify that, we end up with plus or minus 1, plus or minus 13, which if we rewrite it without the pluses and the minuses, we've got 4 possibilities for a rational 0. Okay, and we're just going to start checking. I do not know ahead of time which one of these is going to work. So I'm going to start with, let's start with -1. Okay, so we've got an x to the 4th, we've got an x cubed. I'm just checking for missing terms. We've got an x squared, we've got an x, and we've got a constant. All right, so we don't have any missing terms. So now I'm just going to -7, 7, 29, -29, this is not looking good. -59, 59, yeah, that's not going to add up to 0. So we can cross out -1. Let's try 1. See if that one works. 1, -6, 22, -30, 13, 1, 1, -5, -5, 17, -13. This one's looking good. And yep, we've got 0. Okay, so 1 is a 0, which tells me x minus 1 is a factor. And so this is my remainder, my constant, my x squared, and my x cubed. That's not a small enough degree yet where I can use quadratic techniques to solve it. So what I'm going to do is repeat the process now with this polynomial. So first thing we're going to do is go to the next slide so I have some room to work. So this is what we're doing right now. Our x cubed minus 5x squared 17x minus 13 equals 0. Again, I'm going to list the possible rational zeros. And we're going to divide both of those by plus or minus 1, which again gives me 13, negative 13. We're going to test it again. I think we already tried negative 1, so that's not going to work on this one either. But we still have 1 as a possibility. It could be a repeated root. So let's try 1 again. Mostly I'm just trying to avoid using 13. 1, 1, negative 4, and this is looking good. All right, it turns out that 1 was a double root. So this could give me x squared minus 4x plus 13 equals 0. So now we have this quadratic. So we can use quadratic techniques. So let's just go ahead and use the quadratic formula. Negative, negative 4. So negative b plus or minus 4 times a times c over 2 times a, and then simplify. 4 plus or minus, we've got 16 minus, offhand, let's see, 52. 4 plus or minus the square root, we subtract it, we get negative 36. Plus or minus 6i, right? Divide each of those by 2. 2 plus or minus 3i. Okay, so I have x equals 1 with multiplicity 2, right? Because I have it squared. And then here are my other 2. 2 plus 3i, and notice we have a complex conjugate pair, 2 plus 3i and 2 minus 3i. So there we go. There are our 4 solutions. We started with an x to the 4th, so we needed 4 solutions, and we came up with 4 solutions because the x minus 1 was a double root. It had multiplicity 2. So that accounts for 2 of my roots, and then my complex pair are the other 2. Okay, lots of room to work on this one. Okay, fundamental theorem of algebra basically says what I just said. Kind of backwards. So basically, the degree of the polynomial tells you the number of roots. They could be complex. If you have degree 1, then you're going to have 1 root, and it could be a complex. Not usually. Okay. Linear factorization theorem. You can take any polynomial and write it as linear factors where each of the linear factors has a coefficient of 1, but there could be a coefficient out front that's not counted in this. We're not talking about that. So we're talking about here, here, and here. Those will always have a leading coefficient of 1. And these numbers right here could be real or complex, is what it's saying. Doesn't necessarily have to be real, doesn't necessarily have to be complex. It could be a combination of both. And there's going to be n factors. So if we have x to the 5th power, you have to have 5 factors. Okay. Again, some of them could be complex. Find a 3rd-degree polynomial function with real coefficients that has -3 and I as zeros. And it's telling us that f of 1 equals h. Okay. So what do we know? We know it's 3rd degree. So we're going to end up with an x cubed as our highest power of x. Okay. So f of x, and that also tells us we're going to have 3 linear factors. They told us 2 of them, but they kind of told us a third because this has to come in a pair. So we're going to have some number, we don't know what it is, x minus a -3, and x minus I, but like I said, my I has to come as a pair, so I have to have a plus I as well. Okay. So if I multiply that together, they always want you to multiply it together. I always start with the complex numbers, or the complex factors, I mean. You'll see why in a minute. X squared minus xi plus xi. Because they come in conjugate pairs, the xi's are going to cancel each other out. That's why we always multiply those together first. So we have an x squared minus, but I squared is -1. So that gives me x squared plus 1. So now I have x plus 3, x squared plus 1, and then I got to multiply that as well. X plus 3, x squared plus 1. There's my x cubed, 3x squared, x and 3. So f of x so far is some number, we don't know what it is yet, times x cubed, 3x squared, plus x plus 3. Now sometimes if they had not given us this, then we would have been done. But they did tell us f of 1 is equal to 8. Okay, so what do? We know that f of 1 is equivalent to y. So 8 is my y value, and 1 is my x value. All right, so 8 equals a, I'm going to put these in braces just so that they're more distinct. 1 plus 3 plus 1 plus 3. What do we get? 6, 8. 8 is equal to 8a, which tells me a is equal to 1. And here we go. Our final answer, f of x. A is equal to 1. We've got our x plus 3, x minus I, x plus I, or that's written in factored form, multiplied out, it would just be x cubed 3x squared plus x plus 3. Usually they want it they want it written out. So the bottom one. Okay, Descartes' rule of signs. The number of positive real zeros is either going to be the same as the number of sign changes of f of x. What do we mean by sign changes? So if I have an x cubed minus 4x squared minus 3x plus 2. So this is a positive and this one's negative. So we have a sign change. This is negative and this is also negative. It did not change sign. So they were both negative, so there's no sign change. This one's negative, this one's positive, so we changed sign. So there are two sign changes. Okay, that's what we mean by the number of sign changes. Or less than the number of sign changes by a positive even integer. Okay, so if, say, for example, we had 6 sign changes, then it could be 6 positive real zeros, or take away 2, take away 2, take away 2. It could be any of these combinations. It could be any of those positive real zeros. So there could be 6, not x equals 6, that's not what I'm saying. I'm saying that the zeros, they could have 6 zeros that are positive. They could have 4 zeros that are positive, etc. For negative real zeros, it could be the number of sign changes, only this time we're doing f of negative x, but the same idea. Or less than the number of sign changes by a positive even integer. If it only has one variation in sign, then there will be exactly one negative real zero. Okay, so we need the possible number of positive and the possible number of negative real zeros of this function. Okay, so let's start with the positive. Okay, with the positive, we just do f of x. X to the 4th, 14x cubed, 71x squared, plus 120. Okay, and we're going to count the number of sign changes. So from here to here, we went from a positive to a negative, so there's one sign change. Negative to positive, there's one sign change. Positive to negative, there's one sign change. And negative to positive, there's one sign change. So it could either have 4 positive real zeros, or take away 2 positive real zeros, or take away 2 0 positive real zeros. Okay, so that would be the positive. Okay, now let's look at the negative. So we're going to do the same thing, only this time we're doing f of negative x, and this is for the negative zeros, possible negative zeros. So we plug in negative x minus 14, plug in negative x plus 71, plug in negative x minus 154, negative x plus 120. Simplify that. So negative 1 times negative 1 times negative 1 times negative 1. Long story short, that's going to be a positive 1 x to the fourth. Negative, negative, negative is negative. Times this negative is going to give me positive 14x cubed. Two negatives multiplied are positive. Times a positive is 71x squared. Positive 154x plus 120. Positive, positive, there's 0 sign changes. So, no negative real zeros. Put that together with the total of 4 zeros, and that tells me that they're either going to be positive or complex. Those are the two possibilities. We didn't say anything about complex zeros, but we could have 4 positive. None of them are going to be negative, no negatives. Or 2 positive, 2 complex. Or 0 positive with all 4 are complex. Because none of them are negative. So those are our possibilities. Okay. Time for reflection.